This episode is brought to you by Brilliant. On January 28, 1986, the fatal consequences of misunderstanding a simple component we rely on in multitude became tragically clear. Disintegrating 73 seconds into its flight, the Space Shuttle Challenger disaster brought to the world's attention the critical nature of O-rings. The O-rings in question were two rubber seals, each 3.7 meters in diameter, situated in the aft field joint of the right solid rocket booster. Their function was crucial to prevent hot combustion gases from escaping through the joint during rocket motor operation. The launch temperature that morning was 36 degrees Fahrenheit or about 2 degrees Celsius, significantly below the O-ring's previous flight experience of 53 degrees Fahrenheit or about 12 degrees Celsius. This temperature difference proved critical due to the O-ring material approaching its glass transition temperature, where it became less elastic and more brittle while its ability to respond quickly to deformation was drastically reduced. At ignition, the solid rocket booster segments expand slightly, requiring the O-rings to flex and maintain their seal. However, in these cold conditions, the primary O-ring failed to seat properly within the crucial first milliseconds after ignition. The problem was further compounded by the joint rotating. As internal pressure built up, it caused the joint to flex, expanding the gap the O-rings were meant to seal. Under normal conditions, the O-rings would track this movement, but due to their reduced resiliency, they failed to maintain contact with the metal surfaces. This failure allowed hot combustion gases at temperatures exceeding 5,000 degrees Fahrenheit or about 2,760 degrees Celsius to surge past the primary O-ring. The secondary O-ring, compromised by the same cold conditions, also failed to seal properly. The escaping gases eroded both the O-rings and the surrounding structural material for 59.6 seconds into the flight, growing from an initial breach estimated at 1 millimeter wide. At 73 seconds post-launch, the rigid solid rocket booster aft field joint failed completely. This led to a rapid series of structural failures, ultimately leading to the orbiter and external tank disintegrating. While this tragedy reshaped NASA's approach to safety, design, and risk assessment, it emphasized modern society's critical reliance on these simple sealing components. Early uses of round, resilient rings for sealing date back to the mid-1800s, where unconfined rings were used to limited effect in pistons and telescoping mechanisms that were allowed to slide back and forth. Other variations were the use of large cross-section natural rubber rings used as gaskets for water piping. Thomas Edison's 1882 light bulb patent even demonstrated a round rubber ring at the neck of the glass bulb to keep the mercury in and the air out. In 1896, Swedish inventor J.O. Lundberg patented a design that is considered one of the earliest precursors to the modern O-ring. The modern design variant of the O-ring is credited to Danish machinist Niels Christensen. After coming to America in 1891, Christensen spent decades inventing various mechanical devices, including air brakes for electric streetcars, engines, and starters. In 1933, at the age of 68, Christensen turned his attention to hydraulic system seals. After 4 years of experimentation and testing, he invented the modern O-ring system as a simple yet revolutionary hydraulic seal packing. Christensen filed the patent for the O-ring in 1937 when he was 72 years old. However, like many of his earlier inventions, the O-ring became entangled in patent disputes. During World War II, the U.S. government bought out key military patents, including the O-ring, for widespread use in the war effort. Christensen received an initial payment of $75,000, but the legal battles continued long after his death, ultimately resulting in a $100,000 payment to his heirs in 1971. O-rings fundamentally are a simple class of torus-shaped seals that can be made from a very broad range of materials, such as metals, thermoplastics, and elastomers. They can be made solid, hollow, or even with a hybrid internal structure, though by far the most prolific variant in use has been the solid elastomeric-based O-ring. O-rings are generally designed to function as a component of a fluid sealing system. A typical sealing assembly consists of one or more elastomer O-rings and a feature known as a gland. The gland, usually cut into metal or another rigid material, contains and supports the O-ring. O-ring-based sealing is incredibly versatile in that it can seal over a wide range of pressures, temperatures, and tolerances. They do not require a critical torque or retightening and can be employed in tight spaces with minimal additional component weight. In some applications, O-rings can even be reused, and in non-safety critical situations, when they do fail, it's typically in a gradual and easily identified manner. They're also a highly cost-effective sealing solution. In sealing, an O-ring essentially functions as an incompressible viscous fluid with a very high surface tension. When exposed to pressure from either the surrounding structure or working fluid, the extremely viscous O-ring is forced to flow within the gland to block the flow of the less viscous fluid being sealed, effectively absorbing the stack-up of tolerances within the assembly to create a zero clearance joint. This seal is maintained by the internal memory characteristics of the elastomeric material used. As an O-ring approaches its sealing limit, a failure mode known as extrusion begins to occur. This starts with a small portion of the sealing material entering the narrow gap between the inner and outer members of the gland. When pushed beyond this point, the surface tension of the elastomer is no longer sufficient to resist the flow, and the O-ring material extrudes into the clearance gap, causing a leak. O-ring sealing can be categorized into two application types, static and dynamic, with each having their own respective limitations and failure modes placed on the O-ring. The most basic static seal is the true static seal, in which the mating gland components are not subject to external mechanical motion. Examples of this typically employ the O-ring as a face seal, such as a bolt or rivet seals, plate seals, and pipe flange seals. Captive features such as dovetails are sometimes used on static face seals to aid in installation and maintenance. While true static seals place the least limits on an O-ring, they are uncommon as vibration and external forces are a factor in real-world use, even for seemingly static components. Crush installation seals are another type of static seal in which the O-ring is crushed into space having a cross-section different from that of a standard gland, such as a triangular profile of a tube-fitting boss seal. Crush installation seals require higher part tolerances and assembly considerations in order to keep the O-ring functional when crushed. This method of use is not acceptable by some industries. The surface roughness for statically sealed O-ring surfaces is crucial. These seals require a maximum surface roughness of 0.8 micrometers RMS for liquids, a roughness similar to 320 to 400 grit sandpaper, and 0.4 micrometers RMS for face-type gas seals, or around 500 to 600 grit equivalent. However, the production method is equally important. Surfaces with scratches parallel to the groove, like those from lathe turning, can seal effectively even when rough. Conversely, surfaces with cross-cutting scratches, such as from end milling or routing, require stricter adherence to maximum roughness values. One of the first uses of the precursors to the modern O-ring was a dynamic application known as a reciprocating seal. Reciprocating seals involve back and forth motion along the shaft axis between inner and outer gland elements. This motion causes the O-ring to slide or roll along its sealing surfaces with each cycle. While steam piston seals were one of the first use cases of this configuration, plungers and hydraulic actuator sealing are a more typical modern application. As the O-ring slides or rolls, it flows into the surface irregularities of the mating parts, creating friction. This limits their use to low speeds of around 5 mm per second of travel, and often requires lubrication to prolong their lifespan. Oscillating seals were one of the first modern dynamic sealing applications. In this configuration, one member of the seal assembly moves in an arc around the shaft axis relative to the other member. This classification is characterized by a return in the opposite direction after one or more rotations of travel. Generally, any longitudinal motion in an oscillating seal is insignificant. One of the most common examples of this seal type is the O-ring seal within plumbing valves, such as faucets. Derived from oscillating seals, rotary seals involve one member of the sealing assembly rotating continuously around the shaft axis in a single direction. This classification applies even when rotation is reversible, as it is characterized by continuous motion. Rotary seals rely on their gland size and often lubrication to keep the O-ring from rotating. Their most common applications is in fluid sealing of gearboxes, fixed axles, and motor shafts. One unique dynamic use of O-rings to close a flow passage is known as a seat seal. Unlike other seal types, the sealing action occurs when the closing motion of one component mechanically distorts the O-ring as it compresses it against the seat. The O-ring itself acts as the primary sealing element, directly blocking the flow path when compressed. Seat seals can be further classified into impact and non-impact closures. Common non-impact examples are washer-type seals on plumbing valves, while impact closure examples include floating check valves and seals on solenoid plunger ends. Pneumatic and vacuum seals are special subclassification of O-ring seals. While these sealing systems may look similar to their liquid sealing counterparts, the sealing of gas or vapor drastically affects the O-ring lubrication requirements in dynamic installations and may have to contend with temperature increases due to gas compression. Gas-based sealing also requires lower leakage tolerances, and in the case of multiple O-ring seals, must be designed to prevent trapped gases between rings. O-rings are also sometimes used for non-sealing purposes, such as a wiper that removes debris in reciprocating elements, and as low-power drive belts. Though originally made from natural rubber, the elastomer compounds used in the most common forms of modern O-ring seals are based on synthetic rubbers. Classified as a polymer due to the chemical linking into a long chain-like structure, modern sealing compounds are typically made from 50 to 60% base polymer, with the remainder consisting of fillers, vulcanizing agents, accelerators, and other additives that enhance the polymer's properties for specific applications. The key to an elastomer's performance is the vulcanization process, which creates cross-links between polymer chains. This transforms the material from an uncured or unprocessed plastic-like state to an elastic one. The vulcanization process, including temperature control and post-cure treatments, is critical in achieving the desired physical properties for effective sealing. Once converted to a non-plastic state, an elastomer can, at minimum, stretch to at least double its length without breaking and retract to nearly its original length within 5 minutes after being stretched for 5 minutes. Elastomeric materials for O-rings and seals come in a broad range of chemistries, each with unique properties suited for different applications. Acrylonitrile butadiene, or nitrile, is a popular, cost-effective choice for general use, offering a good resistance to oils and fuels within a temperature range of around 34 degrees Celsius to 121 degrees Celsius, or about 30 degrees Fahrenheit to 250 degrees Fahrenheit. Hydrogenated nitrile improves upon standard nitrile with better heat and chemical resistance, making it suitable for high-pressure applications within -40 Celsius to 149 degrees Celsius, or about -40 Fahrenheit to 300 degrees Fahrenheit. For demanding environments, fluorocarbon seals provide excellent chemical and heat resistance, operating from -26 Celsius to 204 Celsius, or about -15 degrees to 400 degrees Fahrenheit. Silicone seals excel in extreme temperature applications, functioning from -115 degrees Celsius to 232 degrees Celsius, or about -175 to 450 degrees Fahrenheit, but lacks resistance to oil and fuels and has poor tear resistance and low wear resistance. Fluorosilicone combines properties of silicone and fluorocarbon, offering good fuel and oil resistance at low temperatures, functioning from -73 degrees Celsius to 177 degrees Celsius, or about -100 to 350 degrees Fahrenheit. Copolymer ethylene propylene and ethylene propylene diene rubber terrapolymer are particularly useful when sealing phosphate ester hydraulic fluids and in brake systems that use fluids having a glycol base, working well between -57 degrees Celsius and 149 degrees Celsius, or about -70 to 300 degrees Fahrenheit. Chloroprene rubber, or neoprene, provides a good balance of properties, including moderate oil and weather resistance, and operates from -40 degrees Celsius to 121 degrees Celsius, or about -40 to 250 degrees Fahrenheit. For applications requiring high wear resistance, polyurethane is an excellent choice, particularly in dynamic settings, though it has a narrower temperature range of just -40 degrees Celsius to 82 degrees Celsius, or about -40 to 180 degrees Fahrenheit. In the most demanding chemical environments, perfluoroelastomer offers unparalleled resistance and can withstand temperatures from -18 degrees Celsius to 316 degrees Celsius, or about 0 to 600 degrees Fahrenheit, albeit at a higher cost. For specialized needs, butyl provides excellent gas impermeability and is ideal for vacuum applications, and operates between -59 degrees Celsius and 121 degrees Celsius, or about -75 to 250 degrees Fahrenheit. The selection of base polymers for seals primarily depends on system operating temperatures and compatibility with the media to be sealed. These factors must be identified, including any lubricants and potential cleaning fluids and costs. Temperature plays a crucial role in seal performance. High temperatures can cause loss of seal flexibility due to new crosslink formation between polymer chains. This can lead to excessive compression, preventing the seal from returning to its original shape after deformation. Exceeding the normal maximum temperature limit for a given compound always results in reduced service life. In service, elastomers undergo both physical and chemical changes when in contact with sealed media. These changes can occur through absorption of the medium, extraction of compound components, or chemical reactions between the elastomer and the sealed medium. The result is often volume changes, either swelling or shrinkage, depending on the compound, sealed media, temperature, seal shape, and stress conditions. The permissible volume change varies with the application. For static seals, a volume change of 25 to 30% can be tolerated, while in dynamic applications, swelling exceeding 10% is considered excessive, causing friction and wear. Shrinkage, on the other hand, is an unacceptable behavior as it leads to seal failure. Chemical reactions between the seal medium and the elastomer can also cause structural changes, leading to further cross-linking or degradation. Even small chemical changes can significantly alter a seal's physical properties, potentially causing embrittlement and eventual failure. Generally, when an O-ring seal system is designed, the operating parameters of the assembly are established, and an O-ring type that best matches these parameter ranges, as determined by a manufacturer, are selected. Ring selection begins with chemical compatibility. If the fluid causes immediate adverse effects on the O-ring, such as chemical reactions leading to surface destruction or loss of physical properties, the design cannot proceed until this issue is resolved. When multiple fluids are involved, both the exposure sequence and contact duration are considered. Operating temperature is then factored, as this not only affects material selection, but also gland design. For high temperature operations, gland volume may be increased to accommodate O-ring expansion. Conversely, for low temperature use, reducing gland depth can improve sealing by maintaining proper squeeze on the contracted O-ring. Expansion rates of the assembly material must also be factored in for high temperature swings, while typically still maintaining room temperature sealing. In extreme cold operation, special designs like spring-loaded O-rings can further enhance low temperature sealing. Operating pressure is also a significant consideration, as this impacts the material selection, particularly in selecting compound shore hardness. Low pressure applications typically use O-rings of around 50 to 60 shore A hardness, or about that of a tire tread, while higher pressure requires a balance between increased material hardness and gland clearances. Most general-purpose O-rings are around 70 to 80 shore A hardness. The nature of pressure exposure must also be considered. Cyclic pressure fluctuations can cause O-ring extrusion, especially at high peak pressures that may expand the cylinder wall. This failure mode is known as ring nibbling. In the vast majority of applications, a selected O-ring will operate within the physical boundaries where no extrusion will occur. In some more extreme environments, components to reduce the risk of extrusion, called backup devices, are used. These are thin rings of much harder material such as nylon that are fitted into the gland between the seal and the clearance gaps. The need for these devices depend on factors including pressure, elastomer type, shore hardness, clearance gap size, and the anticipated metal part expansion. O-rings are inherently sensitive to the installation process and require a lubricant to protect the O-ring from damage, ensuring proper seating and assembly. This also offers a secondary benefit of providing a protective surface film that extends service life and guard against degradation from environmental factors. In dynamic pneumatic applications, lubrication is essential for wear control, while in vacuum settings, it can reduce leak rates by filling microscopic surface imperfections and lowering elastomer permeation rates. O-rings can even incorporate their own lubricants, such as PTFE or Teflon coatings, and compounds that contain impregnated lubricants, such as graphite, molybdenum disulfide, and powdered PTFE. The assembly process itself is also a key element of O-ring seal design. During installation, the inner diameter stretch is typically limited to 5% or about 25 to 50% of the compound's ultimate elongation or breakage point, in order to avoid compromising the O-ring's lifespan. Twisting must also be avoided, particularly in thinner, large diameter O-rings, and protection against damage is essential during assembly. The gland assembly must be closed without pinching the O-ring at groove corners, and closure must be tightly controlled using a constrained longitudinal motion to prevent misalignment or damage. While O-rings might appear insignificant, their importance lies in their simplicity and effectiveness. They demonstrate that sometimes the most critical components are also the least complex. The O-ring started as an intuitive solution to basic sealing, but over the 20th century, it has evolved into a highly engineered component that is closely tied to its specific application. This evolution took a careful understanding of geometric analysis and its impact on performance. It's a simple fact that engineering and math go hand in hand, and a great way to dive right into mastering your understanding of the fundamental concepts of mathematical analysis is Brilliant. Brilliant is where you discover the thrill of learning with thousands of captivating interactive lessons in math, data analysis, programming, and AI, designed to unleash your potential and transform you into a confident problem solver. Brilliant is an innovative learning platform that stands out for its use of a first principles approach that enables you to build a solid foundation of understanding. Each lesson is brimming with interactive problem solving exercises, allowing you to actively engage with concepts. This technique has been shown to be 6 times more effective than simply viewing lecture videos. Moreover, all of Brilliant's content is developed by a distinguished team of award-winning educators, researchers, and industry experts from prestigious institutions such as MIT, Caltech, Duke, and renowned companies like Microsoft and Google. Brilliant immerses you in active problem solving from the start because truly learning a concept requires more than just watching and memorizing. You need to experience it. By engaging in hands-on learning, you'll not only build real-world knowledge on specific topics, but also develop critical thinking skills that make you a better thinker overall. Investing in daily learning is crucial for personal and professional growth, and Brilliant makes it easy and enjoyable. With engaging bite-sized lessons that fit seamlessly into your schedule, you can build genuine knowledge in just minutes a day. Say goodbye to mindless scrolling and hello to more fulfilling ways of spending your free time. A great foundation point I highly recommend is Brilliant's comprehensive range of math courses that are built for learners of any level, whether you want to brush up on fundamentals or challenge yourself with advanced concepts. In this collection of courses, you'll learn to apply mathematical concepts to business and everyday life while simultaneously enhancing your visual and spatial problem-solving skills, with a strong focus on the essentials, with lessons that highlight the most useful, applicable math concepts. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/newmind or click on the link in the description below. You'll also get 20% off an annual premium subscription.